Welcome back for the second half of Chapter 5 in the Programming Logic and Design book. We're going to pick up with the for loop. In the previous examples, we used a while loop to express iterative logic. In other words, the concept of repeating a set of statements a given number of times. Another construct exists in many programming languages that allows you to express a loop. For example, Visual Basic, Java, C++, they all have a for loop. So a for loop is something that you can use to represent a definite loop. And just a reminder, a definite loop is a loop that iterates a given number of times. So for example, 5 times, 10 times, 8 times. It is known ahead of time. So it cannot be used in the situation where you want to keep looping as long as the user doesn't type XXX or some other outside, looking for some sort of outside input from the user to determine when the loop ends. It needs to be predefined. So whereas a while loop can be used for either type of looping logic, the for loop can only be used for a counter-controlled, also known as definite loop. A lot of programmers like to use it because it's very concise and it allows you to initialize, test, and alter the loop control variable very easily. So if you look at the code examples in pseudocode here, on the left we have the traditional while loop that is used to output the word hello exactly 4 times. So count starts at 0. The first time through count is 0, it outputs hello. This statement here updates count to be equal to 0 plus 1. Count becomes 1. It loops back up around. 1 is less than or equal to 3, and so forth. It continues in this manner until count finally becomes 4. It loops back up here. 4 is no longer less than or equal to 3, so the loop ends. On the right, we have the same logic, the same program essentially written using a for construct. So these are logically equivalent. You'll notice that it starts with the word for. Now in pseudocode, we're going to end the definition of the for loop with end for. When you look at Visual Basic, for example, the terminator will be the word next. So we'll see that in the future. But for pseudocode, we're going to write end for. After the keyword for comes the initialization statement. Count equals 0 initializes count to start at 0, and it also has the test for how many times we're going to go through this. It says start count at 0, go up to 3, and the 3 is inclusive, meaning that when count is 3, it will continue to execute. Once count becomes 4, this for loop will end. Step 1 indicates the value that should be added to count each time through the loop. So each time through the loop, although we don't see a statement here that says count equals count plus 1, this step 1 is handling that. So essentially inside the loop then we can just focus on what is the key logic that we're trying to accomplish in this loop. And this is just reiterating all the points that I made before. If we do not have a step value specified, generally speaking, most programming languages, the default value is step 1. Step value, again, the amount by which control variable changes. As I said, default step value is 1. It can be positive or negative. So interestingly enough, you could start back here, going back to our example. We could start count at 3 and go down to 0 using step -1, and it would work successfully. So as long as we adjust our step value to either positive or negative based on how we're structuring the start and end values, the loop will work successfully. The while loop that we learned about earlier, the while statement, can be used in place of a for statement. Both while and for structures or statements are called pretest loops. That means that the loop control variable is tested before each iteration. This is as opposed to the post-test loop. If you look down at the bottom of this slide, we have an example of a post-test loop implemented with what is called a do-while construct. Notice we have the keyword do, the body of the loop, and in this case we're being very generic and saying pay a bill. This isn't programming code precisely. We're just looking at this in a very high-level general way. Do, and then what it is we want to do, and notice the bottom of this specifies the condition, while more bills remain to be paid. Since the test comes at the bottom, we call this a post-test loop, and post-test loops execute at least one time because the loop control variable is not tested until after we've already executed the body of the loop. This is opposed to pre-test loops that execute 0 or more times. Post-test loops execute 1 or more times. Here we can see an image that describes exactly what I was saying. Here on the left we have a pre-test loop. The test comes at the beginning, so theoretically whatever it is we're testing could evaluate to false and we might never go into the loop body at all. Whereas a post-test loop executes the body of the loop before we get to the test. So the structure you see on the right is a do-while loop, which is a post-test. So what we see here are two different flowcharts and two different sets of pseudocode that correspond to logic that's equivalent. So logically equivalent solutions that would accomplish the same set of steps. So if you look at the left-hand side first, over here, we're using a do-while loop. Notice we're doing the steps in the body of the loop before we test his be true to know whether or not to continue to loop back up to the beginning. What that looks like in pseudocode might be a little easier to understand than the flowchart. We have the keyword do, step A, and again, in this case, we're working in very general steps. A would represent a real programming step. Do A while B is true. So if B is true, we'll loop back up to the word do and continue again. If B is false, we would then exit the loop and proceed to any statements that follow this. If we didn't want to use a post-test loop, we could certainly write this in the traditional way using a pre-test loop. So over here on the right, you can see if we really needed to ensure that we did step A before we tested B, so we needed to make sure we did step A at least one time, we could use a pre-test loop and just make sure that we executed step A prior to the start of the loop. So we're going to do step A up here. Now we're going to use our traditional while loop, while B is true, do step A. And you can see the equivalent down here at the bottom. In my experience programming, most programmers choose to use the pre-test loop and would probably lean a little more towards the solution here on the right, but it is important to know that both pre-test and post-test loops exist. Just make sure you don't use a post-test loop in the scenario where it is not valid to execute A at least one time. If you truly did not want to do that, you want to stick to the pre-test loop where you can have tighter control over executing 0 or more times. So when you're doing these things, just make sure you remember to create your loops as structured. The loop controlling evaluation must provide either the entry or exit to the structure, and the loop controlling evaluation provides the only entry to or exit from the structure. Some languages also support a do until loop. Visual Basic is one of those, which is basically a post-test loop that iterates until the loop controlling evaluation is false. The best example is to go back to something we just looked at here and pick on this one over here. We currently have do A while B is true. If I wanted to implement the same logic but use the do until structure, I would write do A until B is false. I would flip-flop my test here because the until is what we want to use when we are specifying the condition for exit. exiting the loop instead of continuing the loop. Common loop applications. So what are we using loops for? Loops are used anytime we need to loop through and do something multiple times, but it is very common application to use loops to accumulate totals. So for example, think of business reports, where we need to loop through a bunch of records and, calculate some totals. In that case, we can call the variable that gathers those values together, that total, we can call it an accumulator. It's similar to a counter, only in that it's probably, numeric, but instead of starting it at 1 and incrementing one time each time through the loop, an accumulator increments by some value. And honestly, this is best illustrated with an example. So let's see what that looks like. This is a month-end real estate sales report. And what we're looking at is something that, let's say we want to produce with a program, okay? So if you look at this particular output, we have a title up here at the top. Okay, so that would come towards the beginning of the program. We also have some labels, column labels, that we would want to print towards the beginning of the program. And then we have 5 records. And if you look at the records of data, there's some addresses, there's some prices. And in a realistic program, those values would probably come from a database or some sort of other data source. In our programs at this point, we're a little limited where a lot of our data comes from the user typing it in at a keyboard, but the concept is the same. This data comes from somewhere, and our program is going to read the pieces in one at a time, and it's going to display them. So the user is going to provide us an address and a price, and we're going to print them out, and then we're going to get the next address and price. And we're going to continue on in this way until they're done. They've indicated that they're done. And we'll take a look at what that indication looks like shortly. But the interesting thing is at the bottom here, we're displaying a total, and the total actually adds up all of these values. So while we might be tempted to look at this and think the total is calculated one time after the loop that collects all of this, it is true that we will have a single output line that prints the total, but in the loop itself, when we're collecting the values from the user, what we're going to do is add those values one by one as we get them to an accumulator, so that by the time we're done processing records, we have a total that is complete and includes all the prices. So let's take a look at this. Focusing on the flowchart on the left, you'll notice we have some variables. Those are there to either, represent a heading. We have an address and price. Those are going to be used to capture user input. But one of the new things that we haven't really seen yet is this accum price. They called it that to represent an accumulator. You can really call it anything, but it's numeric and it starts at 0. We're going to use that as our bucket, so to speak, to hold the accumulated total of all of those values that we get from the user. And then finally, we have a quit value down here of ZZZ. We're going to keep getting addresses from the user until they type in ZZZ. Once they type in ZZZ, we will stop getting addresses and prices, and we will print the total. So it starts with get ready, and this is interesting because a lot of the book's examples have used housekeeping, detail loop, and here we see a departure from that. That's good because we want to know and understand that housekeeping, detail loop aren't always the names of modules that we're going to use. Here we're going to use get ready. They switched it up a bit, but the concept is the same. We're initializing, we're getting ready. We're going to use it down here. Let's look down here. They put it down here. Doesn't matter the placement in the screen of the flowchart. They placed it down here this time. We're going to output the headers. And then we need to get the first address. Why do we need to get the first address? First address is very important because when we return back up, we're going to compare it to quit. is the address equal to ZZZ? So what we have here is a sentinel controlled loop where address is the sentinel value. So we're going to be comparing the address to ZZZ. If the address is not equal to ZZZ, we're going to go ahead and jump over here into a loop that calls create report. Create report goes on to prompt for the price. We've already asked for the address, so we're not going to get that. And then it outputs it. That output line right there is what gives us our output line here. The orange box is particularly interesting because this is the accumulator portion we were talking about. Accumulator price, if you look in the declaration blocks, started at 0. But here we're setting accum price equal to whatever it was before. The first time through, this will be 0, plus the price the user just gave us. So if the user gave us $150,000, in this step, accum price is updated to $150,000. The next time through, the $310,000 will be added to the $150,000. So the second time through, the accum price will be updated to $460,000. So you're going to see that this value, accum price, will grow because it is in the loop body each time through. It will get larger as each price is iteratively added to it. So this is essential. And then, of course, the last part of create report is to get the next address. So again, address is the loop control variable, so therefore we have to update it. We get the next address before returning back and comparing that address to quit. Finally, once the user types ZZZ, we'll call finish up. This is like end of job in our previous examples, but finally just prints out the word total and accum price. At this point in our program, accum price will include all of the prices added together. We've added them one by one, but at this point they will represent all of them, and we'll get our final value down here. A summary report is similar to what we just saw, but we could maybe just show the totals with no detailed data. This one shows the detailed data as well. So that's one application. Another application of using loops is to validate data. Defensive programming is a term that's often used to describe preparing for all possible errors before they occur. So validating data. So just for example, let's say we write a program that asks the user to type in their birth month. Stop right there. Realistically, our programs would not be command prompt programs. We would probably give them a drop-down list of 1 through 12 to choose from, which is hands down a better way to do things. If you can limit the values that the user can type into acceptable ranges, always do so. However, if you are using a command prompt as we're using today, we would want to validate that the user typed a value between 1 and 12, because if we do not, we fall into that trap of garbage in, garbage out. Meaning that if we get values from the user from somewhere that aren't valid, we can't expect our output to be correct in any manner. So one attempt would be to ask the user for their birth month and check. Say if month is less than 1, in other words, let's say they typed in 0, or the month is greater than 12. And that's a really good idea because you're looking for, okay, was it outside of the acceptable range? And we do see it utilizing our OR logical operator here. That's great. It's a good idea. But the problem is, let's say that it wasn't in range. Well, then we're going to prompt them again and read it a new value in. And that's a great idea. But what if they again type the wrong value? So an if statement's not going to do it for us because it's only going to enable us to check it one time. Else we find ourselves in the pattern of having multiple if statements. And how could we possibly predict how many times they'll mistype it? The better solution is to use a while loop. So we get the month from the user, and while the month is not in range, essentially is what we're checking here, get a new month. This will keep iterating as long as the user's month is invalid. So in a perfect world, the user is going to type in a month that is valid between 1 and 12, and when that is the case, it will completely skip over this while loop because we'll do the check, and the check will fail. It won't be too low, it won't be too high, it'll be just right. So we're going to skip over the while loop altogether. So the idea with the loops in the context of doing data validation is that they're really only going to be executed when we have some sort of problem. The book mentions sometimes we might consider limiting a reprompting loop. So if it goes on forever, we might take a different action. We might override the user's input, or we might maintain a count of the number of reprompts. And then maybe if they mistype the same thing 5 times, we might take a different course of action. So here we're doing exactly that. We're limiting user reprompts. We are going to allow them to mistype or misenter the birth month only 3 times. And the way that we do that is we create a variable called count, and we start it at 0, and every time they type the wrong month, we add 1 to that. The interesting part is by doing so, we can change our condition and say, well, if they mistyped the month, in other words, it's out of range, and that count of attempts is less than 3, well, then we'll give them another opportunity. But once count is no longer less than 3, in other words, they have typed the wrong birth month 3 times incorrectly, we'll go on. Now it doesn't show us what we're going on to, but we'll exit this loop and we will take some other course of action. So this shouldn't be confused with a counter-controlled loop. This is not a counter-controlled loop. It is a sentinel-controlled loop, and the reason why it is we are basing it on something other than a prefixed, predetermined number of iterations. We're not just looping exactly 10 times, for example. It depends on what the user's typing. So don't be confused by this count variable. We're using a counter. Yes, that is true. That is similar. But in this sense, we're using it just to control the number of attempts so that we can keep track of how many attempts were made. Another application of using loops is validating data type. I know that it is common to write a program, run that program, and maybe you're even testing it as the user, and you meant to type in the number 9 and you accidentally typed the letter 0. So in a program, a lot of times if you don't have any kind of validation in there, you could get a runtime error that even crashes your program. So loops can also be used to validate data type, so not just range, but type, such as is numeric. You would want to validate that an age, for example, entered by the user is numeric. And the type of method that you'll use, is numeric, is char, etc., is going to depend on the programming language that you're using. At this point, we're speaking in generalities because we're dealing with pseudocode, but you will find Visual Basic and the other programming languages out there each have their own way to do this, their own functionality built into the language that allows us to test this. What we usually do is we accept user data as strings, and then we convert it to the correct data types. If we verify that it is in fact the data type that we want, if it isn't, we let the user know that, and we often allow them to re-enter the data. So for example, let's say we're working in pseudocode, we ask the user for a salary, and as long as the salary was not numeric, we need to tell them, hey, you messed up, that was an invalid entry, try again, and we get the new salary. So over here in the pseudocode, you can see that we get the first salary while not is numeric. Remember, not will reverse the outcome of whatever is numeric produces. So is numeric will produce a false value if, for example, the user typed in NINE for 9 instead of the numeric 9. So is numeric would produce a false, not would reverse that and make that a true. And we would go in and say invalid entry, NINE is not valid. We could even enter in a little bit more output right here to repeat back what they actually typed. We're not doing that right now, it just says invalid entry. But then we get the next salary, and this will keep repeating as long as the user has not entered a numeric value. So at that point, we just want to make sure we've talked about, validating data type. We've talked about, validated ranges. You just want to make sure your data is reasonable and consistent. Create your programs to be defensive. Try to foresee all possible inconsistencies and errors. And finally, we have a slide here that just does some comparisons between the selection structure and the loop structure. I know working with students, a lot of times these structures are confused, and I could see why. They both start with a decision. They both start with a Boolean expression, right? Well, the pretest loop, anyway, starts with the Boolean expression. So they have that in common, and they also have a set of statements here and here that are executed in the body. This is, the statements executed in the selection structure when the test is true. These are the statements that execute in the loop when the loop test is true. The basic difference between a single alternative selection structure, in other words, one where we only have an action in the yes arm, and a loop structure is that the loop structure repeats. Essentially, a loop structure is a single alternative selection structure that repeats. Here we have an example of a poor choice by a programmer. Let's say we're reading in a series of records, and we want to check and to see if we're at the end of the record. So we input a record. We check, is it the end of file? In other words, was it a valid record, or are we at the end of file? If it's not the end of file, go ahead and display it, get the next record. If it's not the end of file, display it, get the next record. We can't do this using selection structures successfully, even though this is what they started to do. We have no idea how many records there are, and our code is getting very, very lengthy. We will never be able to accommodate all scenarios. A much better approach is to use a loop. Here we input a record. As long as it was not the end of file, a valid record, we display it and get the next one. So anytime we have a scenario where we have repetition, you would want to utilize a loop instead of a selection structure. So that wraps us up for this chapter. Thank you very much for listening.